Yeah, anyway, so when you're running MachLine, all you have to do is compile it, you run the make command, and then we'll pull open a input file, dev input files. Look at this one. No. There we go. Okay, this is what I want. Okay, so this is what the input file looks like. We're missing the post-processing section.
I think you need an underscore between post and processing.
I think it's a dash.
What was it?
Could be wrong. This is why you document.
Are you changing your syntax on this?
Oh, no, it's an underscore. All right. Okay. Okay, so this is the input file. It's going to pull in this. I don't know if I want to use very fine delta wing. Let's see what other options do we have. LS dev meshes. We'll go with delta wing medium.btk. Wait. Okay, so we tell it what our mesh file is. Here is where we'd also specify mirroring if we want to do that, in our singularity order, stuff like that. Then we give it information about our wake model, which the options that we have here are, we tell it whether or not a wake is present. So you have some situations where you know there isn't going to be a wake. For example, like symmetric profiles at zero angle of attack, or a spindle or a sphere, you know there's not going to be a wake. And so you can explicitly tell it that. You can also tell it whether or not to append a wake. So in supersonic flow, even if there is a wake present, even if there is a discontinuity in doublet strength at the trailing edge, it doesn't matter for some configurations. And so you can explicitly tell it, yeah, there's a wake, but don't bother appending it because it makes no difference. And then you can specify directly what the test distance is. We can also put in our matrix solver. Here's an option to be able to write out the A and B matrices. And then our post-processing options.
On the trust distance, you have 20. What, like, is that like, how's that? What are the units, or how is it defined?
Mesh units. What are the meshes? MachLine is entirely ignorant of units.
Okay, so but like how does it know what the distance is with the number 20 then?
It's whatever the units are for the mesh. Or so it's so if like your mesh is defined in some scale. So you've got your leading edge at like 0 and your trailing edge at 1.
Okay, gotcha.
Your treff distance will be at 20. It's just going off of whatever the mesh is scaled to.
Okay. And that treff distance is the distance that the wake goes back right before it stops.
Yeah. Yeah, so that's the point at which we stop modeling the wake. And these are our out points. I'm just going to call these deltawing.btk. And I'm just going to have it output all of them for right now. And then I'll go through and show you what they look like. I need to make sure that, yeah, okay, we do have sample points there. Okay. So now I've got my input file specified. All I have to do is give it the call up the MachLine executable, and then give it the path to my input file, and it will run. And voila, we're done. So we can see that I didn't specify verbose, and so it defaulted to true. I got my input file, and it's giving me all this information. It's telling me how many vertices, panels, edges it found. It's calculating parameters. It'll tell me that it cloned 37 vertices and that there's now this many vertices. It placed control points here, and then it'll solve the system. And then it tells me, well, this is the maximum my residual I got out of here. 10 to the negative 13th is that's on par. Depending on your configuration and the solver you're using, this can be as high as probably about 10 to the negative 9th. Anything higher than that, you should really be questioning what you've done. Yeah. LU decomposition will drive this down to about 10 to the negative 16th, which is really nice, but it takes freaking forever. And then it'll give you your maximum minimum pressure coefficients and report the forces for you. Now, like I said, you don't want to bother having to parse all this out of here, so we can just pull open this results file, or the report file, sorry. And this tells us everything. So we've got generated by MachLine, gives us the day and time stamp for when we ran it, all of our information about the mesh. It'll tell us our solver results, how long things took. See, we ran GMRes in, what is that, 2/100ths of a second? It's pretty good. The number of iterations it took, which like GMRes is just such a cool algorithm. Do you know about GMRes? It's awesome. Anyway, and the residual and whatnot. So basically everything we saw in the terminal has been stored in this report file for us. And it's stored as a JSON, so we can really easily read that back into Fortran or into a Python script and analyze that data. So in a lot of my studies, I'm going through and studying convergence of force coefficients. So I'm running a bunch of cases, and then I'll go through and pull open their report files and just pull out these force coefficients, because that's all I need. And then total moments as well. And then it will also give you your full input. So whatever was in your input here gets copied back out to the report file, so you know exactly what you ran. Yeah, I thought so. I hope it's useful. And then it'll tell you what the total runtime was. So that's the report file.
Take off, Corey.
Okay, sounds good. Thanks, Jeff. I forgot to delete this X here. So this is where we tell it the off-body points that we want our potentials written out to. So I give it a file that has a bunch of points, and then it will, so it's going to read the points in from this file, and then it's going to output the potentials to this file. So you have to have two files there. One where, so you're telling it, my points are here. The next one you're telling it, write it out there. Anyway, we'll look at that in a second. Well, let's pull open the body file. So if we open up Paraview, and these are all just stored in VTK format. VTK is just a convenient unstructured data format, and it's used with Paraview. So we're dev results deltawing.vtk. It's the one we just ran. And voila. So this is our result that we just got out of MachLine. That's our doublet distribution over the surface. We can look and see this is our source distribution. Notice it's a lot simpler. Again, source strengths are only due to geometry and free stream condition. We can also look at our pressure coefficient distribution. So over the leading edge, we have relatively high pressures. Over the trailing edge, we have low pressures. And you can see that that Mach cone coming off of these points at the root are giving us variations in pressure coefficient. And then there's also other information. This is telling us, what distribution order. All of these are first order or lower order panels, so that's fairly standard. This is giving us the telling us what our normal vectors are on here. Again, nothing too special about that. This is phi sub u is our total external potential. So if I wanted to, I could use Paraview, take this, calculate a gradient, and it would give me my surface velocities. These are my surface velocities on my panels. You can say they look a lot like pressure coefficients. Who would have thought? You calculate pressure coefficients from velocities. And that's really it. We also have a wake file that we've output, and that's our wake. So in this case, our wake is just perfectly aligned because we're at zero angle of attack. If I rescale my doublet distribution, you can see there's quite a bit of variation in our wake strength, but it's on the order of 10 to the negative 11. So that's really nothing. So this is one case where I could tell MachLine, there really is no wake, don't bother modeling it. And it would work just fine. If I go back in here to my input and I give it a y or z velocity, y velocity. So I give it some finite y velocity and rerun the case. Oh, it's doing the off-body calculations now. But it's already written these out, so we can look at those while it's working on that. If I reload these, then you can see it's now changed angle because it's aligning itself with the free stream. And now we actually do have some significant variation in the wake, but it's well behaved as we would expect. And then if I look at my pressure coefficients on my, oh wait, let me reload.
Your pressure coefficient, your maximum pressure coefficient is 0.69.
0.57 here.
Isn't that a little low for a compressible run?
No, that's about what I expect.
I thought stagnation pressure was higher than one compressible.
But we're not ever hitting stagnation here.
Oh, okay, pointy nose.
Yes. Yeah, so now that we've got some finite angle of attack, we can see that our pressure distribution on the bottom is different than our pressure distribution on the top. So we are going to generate lift here, which is nice. You know, aerodynamics works. We can also look at the control points. So now this will spit out for us. I'm going to turn off the wake. This will spit out for us all of our control points. We can make those a little bit bigger. These right now are colored by the boundary condition type. So they all have the exact same boundary condition type because we use the Marino formulation and there's no mirroring. But if we were using mirroring, you would see there'd be a line along the middle where there's a bunch of strength matching boundary conditions. You can also color them by the residual, which the residual is never, the greatest residual is 1.3 times 10 to the negative 13th. But this is sometimes useful for figuring out, you know, where are the problematic points in your mesh for being able to get a good solution out of the linear system equations. I've noticed that on geometries like this, the residuals tend to be a little bit higher towards the nose. I don't know why, but anyway. So that's the control points. And then, lovely, it's done. So it's calculated all these potentials at some off-body points. So we can now read these into Paraview. Delta wing image sample points. CSV reader. Why we have to do a few filters here. Table 2 points. And here I tell it that my X column is X. You would think it would automatically detect this a little better, but I guess not. Okay, so now I've turned this table of data into a set of points. And I can turn on those points. So now I've got, and here I've just been sampling. I wanted to sample the potentials at the trailing edge. So now I can look and see. Oh dear. It froze on me. I may have just crashed Paraview. All right. Well, this is awkward. Anyway, so these are all the points at which I told MachLine to give me my induced potentials and whatnot. If Paraview decides to unfreeze, then I can change the coloring of them based on these calculated potentials. Gee whiz, what is it doing? Okay, we're just going to do it. Paraview. Force quit. Okay. We're going to try this again. Okay, this time we will just open Delta Wing and my sample points. Filters. Oh, I need to redo my favorites. I had all those set up. Table points. I learned this from taking Dr. Spall's Udemy CFD course. Good recommendation.
Yeah,
Yeah.
is that where you learn Paraview?
Yeah.
Well, I'm glad we're recording this because I'm gonna snip out this portion of it and post it separately, so,
I like it. That'll be good.
yeah.
Okay. Okay. Just don't do it on the, anyway. Let's go back to pressure coefficient here. Anyway, so this table's points, I can now color it. Capital Phi is my total potential. Lowercase phi is my perturbation potential. Phi d is my doublet induced potential. Phi infinity is my free stream potential, and phi plus is my source potential. So I can look at these and see, how do these look? And rather than having this just be a bunch of points, I can do a Delaunay 3D filter. There's always, no, that's on the Delaunay 2D. Okay, apply. This takes a second to run, but it's going to turn all these points into a solid. There we go. So now I can see a little more clearly what's going on here. And if I wanted to, I could come and I could slice this solid and have a look at what's going on inside. But I can see this is my free stream potential. Obviously, the free stream potential doesn't show that the body's there at all. My doublet induced potential.
Shows you this.
What's that?
That show you basically there's a big difference. Or the difference.
Yeah. Yeah, and so you're seeing here that this is where my wake is coming off, and I've got some potential here underneath, some potential here above, and my wake is the dividing line between the two. If I look at my total induced potential, then it's going to look like that again. But what we should see is inside of the configuration, and we really don't have the density here to look at it like I would want to. But what we should see inside the configuration is that the total induced potential is pretty much zero inside, which if I do probe points here, I'm looking at this. So my induced potential here inside the configuration is about 0.001, so anywhere 1,000. Now remember, this is not at a control point. So the solver hasn't been asked to enforce zero perturbation potential exactly at that point. So that's one of the limitations of these Dirichlet approaches is that, at a finite number of points, we've said enforce zero internal perturbation potential. But just because we've done it at that many points doesn't mean it's going to be true everywhere. It's going to be decent, but it's not going to be true everywhere. Okay, that's pretty much it for outputs. Was there more you were wanting to see?
You want to show them a slice, Corey?
Oh yeah,
slice.
I can show you guys that. So if I want to plot a pressure slice over this wing, yeah, if you're gonna post a tutorial, I might as well do a full tutorial. What I can do is I can selecting this delta wing mesh. I'm going to stop showing my points. I can set up a slice, and I want the normal to go out the side of it. And let's do, oh, that's not out the side. There we go. Okay. My origin, I just want to be right at the middle. Apply. There we go. Now I've got this little slice, and I can take that. Ooh. So, plot data. Apply. Aha, now I've got this data plot. And attribute type, I want to plot point data. That's fine. Actually, no, I want to plot cell data. I want to plot the pressure coefficient. So I'm going to deselect all these other ones. And then you can see it's really not looking very good right now, but that's because we're plotting against the point index as opposed to the actual point location. So if I come down here to, gee, I thought it was higher up than that. I don't have all of my options.
Use index for X.
Ah, there we go. So rather than using index for x-axis, I come in and I tell it I want to use the x coordinate of the centroid for my x-axis. And there we go. So this is my pressure distribution over this slice. And you can see there's a difference in pressure between the upper and lower surfaces. It's kind of jagged, like we were talking about during that meeting with the Air Force yesterday. But that's how we can plot slices of data. And I think there's something down here where you can invert the y-axis, and so plotting pressures kind of more as is standard. But yeah, that's about it for
Can you
Paraview.
go back on that slice and now drag it along the wing and it'll update this? Or
I
do you
think
have to create a new slice?
I think so, yeah. So if I go to my slice and let's see.
Yeah, if you just pull that, Corey, then it will, yeah, you can do all sorts of stuff with it. The origin, you can also change the origin there.
Yeah, so I can pull it over this way, apply.
And you just have to update everything.
How do I update that? No, that's what we were looking at before. How do I tell plot data to update now?
I'm not sure you drug it in the Z direction. I think you might have drug it in the X direction.
Did a little bit. Oh,
That's going down. It's making your box. I'm not sure if that's just staying on the same plane though.
Oh, it is staying on the same plane.
yeah.
So I'll just manually
Just
set this,
type
go out to
in
like
comma,
0.2.
There we go.
There you go.
There we go. And now it updates over there. Yeah.
Cool.
Pretty nifty,
Yeah, Paraview is crazy powerful and crazy confusing the first time you use it.
eh? Yes.
It's a lot to swallow.
Yeah, the nice thing about Paraview is it's all got a Python, it has Python interface to it. If you go into the MachLine folder and go into studies, a lot of those all of those studies use the automatic Python Paraview interface. And so rather than having to come in here and manually extract all this data, you can just do that through a Python script.
I also figured out how to do that on Windows.
You did?
I did.
You're the man, Jeremy.
Isn't there like a record macro too? So you can come in and do all this manipulation by hand, record this macro, and then it'll output the Python script or something to do that automatically in the future.
Yeah, so if you go to tools and click start trace, then that will, and you just hit OK, that'll start again tracking everything you're doing, and then you go up to tools and click stop trace, and it'll bring up a window that has a Python script that lists out everything that you've done in Python. And so you can just take that and copy and paste that into your code. Yeah, it's pretty sweet. It records a lot of unnecessary stuff, so you have to do some tweaking with it.
Like your mouse moved from this location to that location.
Not quite that unnecessary, but pretty close, yeah. So yeah, that's Paraview. That's the outputs for MachLine.
Question, how far in like the flow field, how far away does the MachLine output the like potentials?
As far as you want.
And you set that, is that the same as the 20 something line for the weight?
No, that's just a function of what you put in here for your points, your off-body points that you want this at.
So, off-body points is like outside.
Yeah, so if you put in something here for off-body points, you can put in whatever points you want, MachLine will calculate it. So I could have something, a million miles away from my wing, and
But it doesn't generate that. We have to make that.
It's a sample. So usually you call this sampling. Yeah, and he's got sample points. So once MachLine has developed this solution, you can now sample the domain anywhere, rather, because it's only, MachLine is only a surface mesh.
Mhm.
You know, doesn't have a volume, there's no limits to its volume, so you can sample now the solution at any point outside of this.
And
Then you
that's,
put it in through that CSV file, you tell it what locations you want to sample it at. And then that data can be read into Paraview or post-processed however you want. I mean, it's just a CSV file of information that will come out later with the sample.
and that's usually just like a 3D grid.
Doesn't have to be, it can be a
Or
line
plane or
sometimes.
line.
Yeah, so in the supersonic stuff that we're doing, often you'll sample below the aircraft, you'll get pressure below the aircraft, because that's gonna tell you what your supersonic boom is gonna sound like, this pressure distribution below the aircraft. So we go, you know, like 5 body lengths below it or something, and sample a straight line there, and then you can plot and you can see this M-type wave coming off of the aircraft for pressure that's gonna turn into noise.
You'll be doing that a lot.
Good to know.
And
Kind
by,
of fun, be kind of fun to sample a vertical plane though, downstream, and you might be able to see the Mach cone on something, right?
yeah,
So you could see that, you know, the circular cone hitting that plane.